Hello everyone, this is second video. At this video we want to talk about number conversions using the radix formula. But first, let's talk about the word radix. Base of a number may sometimes be called radix of a number, and the word R in the formula below stands for the word radix, and the formula is called the radix formula. As you can see, this is actually the radix formula. It has both integer part and the fractional part. So if this is our radix formula, all of the positive powers, I mean n, n minus 1, r1, and here we have r0, is called the integer part, and all of the negative power parts are called the fractional part. So in any number, as you know, we may have an integer part, or we may have a fractional part, or we may have both of them at the same time. In everyday life, we almost never write a number with its radix formula, but we write only the coefficient parts. For example, when we have 6492 as a number, we can totally understand that 2 is in ones and 9 is tens and so on. So the place of a number defines its weight. So when we have 6492, we actually only have written the coefficients. So 6 is A3, 4 is A2, 9 is A1, and 2 is A0. Same is true for the fractional part, of course. For example, in the number 1.748 in decimal, it's obvious that 1 is ones, 7 is 1/10, and so on. So in this case, the coefficients would be A1 dot A minus 1, A minus 2, and A minus 3. Other bases to base 10 conversion. You know, the radix formula plays a critical role in this conversion. We just put the number in other base into the radix formula and calculate it. That's it. Check these examples. Now, before the examples, let me tell you, you may want to convert a number from hexadecimal to base 10, or an octal to decimal, or a binary to decimal, and we just use the radix formula, like the examples here. For example, 5.12 at base 8 must be converted to base 10. We just write the radix formula. R is 8 here, so we place R's and we just calculate what comes up. 5 and 0.125 and this one, which is too long actually, and we get to this number 5.15625. The same number could be in base 16, for example here, and then the radix formula would be 5 by 16 to the power of 0 plus 1 by 16 to the power of minus 1, and so on. We actually calculate what we have here, write them down, and add them up. We may also have a binary number converted to base 10, which would be something like this. Writing the radix formula of binary, we get 8 plus 4 plus 0 plus 1 as the integer part, and for the fractional part we get 0 plus 1/4, which gives 13.25 in base 10. One thing to remember is that the higher the base, the higher the value of the same number. Let's say we have a number 100.11 in base 2. It adds up to 4.75. If the same number was in base 8, it would be 64.14, which is rather higher than base 2. Although the number itself is the same, however, the base causes the increase. If the number was in base 10, it would be 100.11, obviously. And we just check this number in base 16. It would add up to 256.066400625. So as you see, the higher the base of a number, the higher the value it creates. Now we want to talk about how to convert a decimal number to another base. First, we equate the decimal number with the radix formula of the base we want to convert it to. Let's say our number is decimal k and we want to take it to base r. At first, we don't know how many digits the destination number is going to have, so we write a formula like this. K is equal to a0 plus a1 multiplied by r to the power of 1. Now we have r here. R is our destination r. We factor out r and we factor out r from these terms, only these terms. And then we divide each term by r. You know, we have a small formula here. In an everyday division operation, we get a quotient q and we get a remainder r. So dividing k by r gives us the first quotient, let's call it q1, and the first remainder, let's call it r1. The relation is like this. These two relationships are going to be equated. By equating these two relations, we get a0. You know, as you see here, we have an r1 and we have an a0 here. They seem to have a relation. a0 is r1 and q1 is equal to the rest of this part. So the next step is to equate the remaining terms. You know, here we have found a0, so this term can be omitted from both sides of the equation. Now we're dealing with q1 part and the remaining of a1 and a2 by r1 and so on. At this formula that we have here, we've again factor out r and divide by r. And we get to something like this. This time we find a1, which is equal to r2. See, now we have a1, it's already revealed, and q2 is for the remaining of the sentences. As we can see here, the second remainder will reveal second coefficient of the target base number. We continue this process until we get a zero quotient. You know, we continue until the quotient part of the division is 0. That would be end of the conversion. I will show this with an example. Also remember that this process is used only to convert the integer part of the number. If our number has fractional part, the fractional part needs to be converted separately. and the process of converting it will be covered after the examples I give for the integer part. So first, let's see some examples of this. We have an example of decimal to hexadecimal conversion. 146 in base 10 is equal to what in 16? 146 must be first divided by 16. We get a 9 as a quotient plus a 2 on 16 as a remainder. So our first remainder is 2 and our first quotient is 9. Next, we use the first quotient and we divide it by 16. We get a 0 plus a 9 as a remainder. So the Q2 is 0, so the second remainder will be A1 and the process of conversion is over. Why it's over? Because our quotient is 0. So the number in total, it will be A1, A0, which is a 9-2 in base 16. Now let's see another example, decimal to octal conversion. For example, 67 decimal needs to be converted to octal. 67 is divided by 8 because 8 is our destination radix. We get an 8 as a quotient and a 3 as a remainder. So our A0 of the target number is 3 and the first quotient is 8. So we jump to the next step, which is to divide 8 by 8, which gets us a 1 and a 0 as a remainder. So the second remainder is 0, which gives us the second digit of the octal number. Also, we have a quotient which is not 0 yet, so we continue our division. By dividing 1 by 8, we get a 0 as a quotient and we get a 1 as a remainder. So the third remainder is 1, and since the third equation is 0, then the conversion is over. We have A2 as 1 and the quotient is 0. So our number will be 103 in base 8. Decimal to binary conversion. This is another example. We have 14 in decimal and we want to convert it to binary. Our first quotient will be 7 and the first remainder is 0. So we have found our first coefficient. Then the second quotient is 3 and the second remainder is 1. So we have found A1. Again, dividing the second quotient by 2, we get 1 as a quotient and 1 as a remainder. So we have found A2. And finally, dividing third quotient by 2, we get 0 as a quotient and we get 1 as a remainder. So A3 is found. Our number would be 1110 in base 2. Now let's talk about the fractional part conversion, decimal to other bases. Similar to converting the integer part, fractional part conversion also starts by the radix formula. However, in this case we multiply it instead of division. But why? We will see shortly. Let's assume that we have already converted the integer part and now we're left with the fractional part. So the radix formula will be something like this. A minus 1 multiplied by r to the minus 1 and so on. if j is the fractional part of the number, we equate j and the fractional part of the radix formula, something like this. And then in order to find a minus 1, the first one that we want to find, we must get rid of r to the power of minus 1. And to do that, we multiply both sides of the equation by r. So as you can see, multiplying both sides by r actually eliminates r because it gives r a power of 0, which is equal to 1. So now we see that a minus 1 is actually the integer part of a number that comes up here. Doing that, we actually pull out a minus 1, and it's now an integer because it's with r0. So a minus 1 is the integer part of jr, which now has both integer and fractional parts. The integer part is equal to a minus 1. In order to find a minus 2, we need to multiply the remaining fraction by r once again. Let's see the entire process with some examples. (0.214) needs to be converted to base 16. What we do first, we first multiply 0.212 by 16. We get 3.424. So 3 is our a minus 1. Next, we actually take out 3. We don't need it anymore. We have found a minus 1. Now we want to continue in order to find a minus 2 and so on. So by taking out 3 from this number, we're left with 0.424 multiplied by 16. We get a 6 here, which is our a minus 2. And then if we continue the process, we get a 12, which is a C in hexadecimal, and which is our A3. Continuing this process, we get an 8, which is a minus 4, and then we get an 11, which is a B. You see, as we continue, the number never ends. We write a minus 1, a minus 2, until a minus 5, and we put 3 dots here, showing that the number continues. You know, note that although the source number has finite digits, our destination number doesn't need to have finite digits. Now, another example converting decimal to octal. 0.4 multiplying 0.4 by 8 gives us 3.2, which actually reveals a minus 1 equal to 3. And then the 0.2 part is multiplied again by 8, which reveals that a minus 2 is 1. By continuing this process, we get a minus 3, which is 4, and we get a minus 4, which is 6. As we continue, we see that some numbers are repeated. 0.4 by 8, which gives 3.2, is actually being repeated here. Our a minus 5 is 3, that's okay. However, there is a repetition going on here. So seems like if we continue our operation, we get repeated numbers over and over. For example, if we move on, once again, we see another repetition happening here. And now we can totally see the repetition process here. 3146 is going to be repeated again and again. So we can write it with a bar over our numbers. The bar shows the repetition. Decimal to binary conversion. We multiply the number by 2. So our first a minus 1 is 0. We continue the process. We get a minus 2 as 1. We take out 1. Here actually we can't take out 0 from 0, so we don't take out anything. We come to the next stage, and here we have a 1 as an integer. We take out 1, and we continue multiplication until we get a minus 3, which is 1, and a minus 4 is also a 1, a minus 5 is 0, and a minus 6 is 1. Actually, we don't need to continue this anymore. So we have got our coefficients, we write them, and that's it. That's our binary number. The 3 dots here shows that the conversion can be continued, however, we don't need it here. So this is how numbers work. In decimal case, starting from 0, we get to 9. In octal case, the same number continues until we get to 7, and then we jump to 1, 0, and the counting continues. In hexadecimal case, our numbers are from 0 to F, and in binary, our numbers grow like this. And that puts an end to this video. I hope you liked the video, and I'd be very happy if you subscribe to the channel and turn on the ring bell. Also, like the video and write your comments if there are any.